Today we'll take a look at a pretty important concept, which is image registration. Okay, as I gave you a brief motivation last time, in computer vision, what we do is first we align an incoming image. So for example, let's say we were doing face recognition. Okay. Then our camera grabbed some picture, okay, of some person, right? Okay, so as we grab this frame, we need to do two things. We need to do detection first. For example, in case of face recognition, we need to do face detection, meaning where's the face. So I'll show you a few detection algorithms later. But for right now, let's pretend somehow we are able to detect where the face is, right? So after we do the face detection, then the next step will be to do the image registration. Okay. So this is needed to enhance recognition accuracy. We can skip this part for face recognition, but for medical image analysis, we still need to align the two images. So when we do the registration, the concept is like this. We have a reference image or a reference face as an example, which is perfectly straight. Okay, just the face, nothing else. Okay, so then what we do is we determine the correspondences. Okay, so as part of this registration, first determine correspondences, meaning you need a few points in the two images. So if this is our incoming image, okay, so for example, what we need to do is we need to know where the eye is. So that could be one of the correspondence points. So this could be one correspondence point, another correspondence point. So this is point corresponding to this one. If we can figure out this point corresponds to this point, okay. Same way if we can figure out, for example, the tip of the nose, chin over here. So if we can get 4, 5, 6, 7 of these corresponding points, then as I will show you through a mathematical technique that we will develop, then we can rotate, scale, make it perfectly same size, same orientation as the reference image. And then once we have done the image registration, then we can go and do the recognition. So today's lecture will focus on the registration part and developing the theory for it, and then you guys will do this as part of the next assignment, implement the code, and see how you can align the two images given a reference image, right? Okay, so if we know the correspondences, so if we know correspondences of a few points between two images, okay, we can determine the rotation, scale, and translation needed to align the incoming image with the reference image. So that's the approach we'll follow. Okay. Okay, how do we know the correspondences? Then we'll go into another technique later on, But for today's lecture, we'll assume we know where the eye is, for example, we know where the right eye is, we know where the nose is, we know. So then, based on this knowledge that these 4 or 5 points correspond to our 4 or 5 points in the reference image, what rotation, what scaling, translation is another technical term for a simple shift. So translation basically means shift. Like shift in X and shift in Y. Okay. Scale basically means zoom in, zoom out, right? Rotation, rotated. So you can see in this particular case, this face is a little bit tilted to the right, so we can make it completely straight. Okay, so let me go one step at a time. First show you how do we rotate, how do we scale, how do we translate one image, so what's the theory behind it. Then we'll go into developing the registration theory. Once we've developed the registration theory, then I'll talk about the implementation code. Okay, so first let's take a look at rotation of images. Okay, so let's say we have a point on the circle, okay, of some radius r. So this is some radius r. So we put the r over here. Okay, at some angle alpha. Okay, so then there's a standard mathematical concept. The x, y coordinates of this particular point are given as x value is r cosine alpha, y value is r sine of alpha. Okay, so whatever this y is over here, so this is our y, this is our x. So based on the angle alpha, we can determine the projection of this point on the x-axis and the y-axis. Okay, now let's talk about rotation. So let's pretend this point over here got rotated to another point over here. Suppose the coordinate of that point is x prime, y prime. So xy got rotated by an angle theta. Okay, so what we want to know is we want to express x prime, y prime in terms of x and y, right? So if you take a look at what will be the x prime, what's the total angle? See, alpha was the angle from the x-axis to the xy point. Then further, there's one more theta angle to go to rotate this point to x prime, y prime. So as far as the x coordinate x prime is concerned, as you can see, this will be r times cosine of, what's the total angle now?
Alpha plus theta.
Alpha plus theta, right? And very similarly, y will be, y prime will be r sine of alpha plus theta, correct? Okay, if I expand it, you will see this is r cosine alpha
Cos theta
minus r sine alpha sine theta. Okay, very similarly, let me expand this. This would be r sine alpha sine theta plus r cosine alpha sine theta. Right, so all I did is just do a trigonometric expansion of cosine of alpha plus theta and sine of alpha plus theta. Okay.
I think, Professor, it should be sine cos here.
Yeah.
I was just looking on Google.
Wait, this should be
Sine and cos.
sine and cosine. Thank you. Okay, so sine alpha, cosine theta, or cosine alpha, sine theta, right? Okay, so now we already know that x is given by r cosine alpha, and y is given by r sine alpha. So if you take a look at this one, what will this become?
The x,
This will become
the
y,
y,
and this will become
x.
x. So I can write this as x cosine theta minus r sine alpha is y sine theta, correct? Y prime will very similarly become y cosine theta minus x sine theta. Did I make a mistake? R sine alpha is y, r cosine alpha is x, right?
The sign is minus.
Oh, plus. Okay. Okay, so anyway, now let's try to write it in matrix form. In matrix form, x prime, y prime. Okay, if I write the first equation, this will be cosine theta minus sine theta, x and y, right? So x cosine theta minus y sine theta. So that gives me the first equation. Everybody agrees? Okay, let's take a look at the second equation. What's x being multiplied with? Sine theta. And what's y being multiplied with? Cosine theta. Okay, so anyway, this is 100% same. So if we wanted, so if we were given, for example, let's say in an image, okay, here's the person, okay. Okay, and let's say we are given this, or let me make it easier. Okay, let's say the person is looking like this, right? Okay. Okay, as you can see, there's a rotation involved over here. So there's an angle theta involved over here. So what does that mean? Every pixel here now should be rotated right. So whichever pixel we pick, let's say I pick this pixel, and the coordinate of this pixel is x of, let's say, 50, y of 75, because remember in images the top left is 0, 0, x-axis goes this way, y-axis goes this way, right? So if this particular point had a coordinate of this, and suppose the rotation is, let's say, 5 degrees. Sorry, 5 degrees. Okay, then where will this point move to? So if we plug in theta of 5 and compute this, multiply it with x, y, so that will be the new location of that point. Okay, so this tells us how each and every point over here, so if it's a 100 by 100 image, to every point you will apply this transformation and it will make it whatever rotation we indicated over here. Okay, so very similarly, okay, sometimes we have a scale involved, meaning the image was smaller or it was bigger, we need to zoom in or zoom out. So if scale is involved, scale indicates zooming, then basically this becomes, so if this was R, this will become basically R times S. S is our scale as we rotate it. So then if we go through the math, basically what happens is S shows up over here. So whatever that zooming factor is. Okay, so it becomes S cosine theta, S sine theta, and so on. Okay, if there's a shift involved, meaning this point gets shifted to the right, so let's say it got shifted to the right, So shift is very easy because all we have to do is whatever is the X shift, suppose we call it T1, T2, T for translation. As I indicated, translation is terminology we use for shifting. So shift in the X, shift in the right. So anyway, if this was the image given to you, okay, if there was a T1 of, let's say, 10, that means every pixel over here will get shifted to the right by 10 pixels. Okay. If there was a Y shift up or down, that will be indicated by T2. So this is our basically transformation matrix, which will move XY pixel. So XY once again is not the value of the pixel, it's the location of the pixel. So that location will be scaled or shifted or rotated based on the theta according to this particular map. Okay? So once again, if you are given two images, let's say we knew that this rotation is, let's say, -5 degrees. Okay. So meaning, see if I draw the eyes, so this is -5 degrees from the x-axis. Okay. So if we need the rotation, and let's pretend scale we need it to be 1.2, because we need a 20% zooming in to make it same as the reference image. Okay. And let's pretend we needed to shift it left by, let's say, 15 pixels, move it up so that we can just cut out that face. So if T1 is -15, T2 is -20, 20 pixels up. So if we apply this to every pixel in this image and then cut out in the corner, that will basically register, meaning align this image with our reference image. So that's how we will accomplish it, right? Okay, so that our math becomes a lot more easier, our coding becomes a lot more easier. What we'll do is we'll define S cosine theta to be some variable A. Define minus S sine theta to be some variable B. Okay, if I do that, then what happens to this equation? X prime, Y prime becomes, okay, what is this now? A. What is this? B. Okay, how are these two related? Minus B. And this is the same as A. Then XY. And then T1, T2. Okay, so this is our transformation in 2 dimensions, given certain rotation, scaling, shifting. So once again, if we apply it to every pixel, provided we know what is A, what is B, what is T1, T2, we'll be able to rotate, scale, shift to however we want it. Okay? So now the challenge is, so here's the challenge. Okay, given a set of correspondences, okay, we have to determine A, B, T1, T2. Okay, so let's once again assume we were given a reference image. We know the exact location of the eyes, the nose, the chin, and maybe a few other points. Okay, so for example, we know the left eye occurs, let's pretend at X of 20, Y of 25, so this is our left eye. Okay, let's pretend somehow, okay, and then we will fill in the somehow later on, is in our incoming image, the left eye is at x of 72, y of 85. Let's pretend. So if I go from here to here, here to here, that's 7285. Same way, let's pretend we know the location of right eye over here. We know the location of right eye. We know the location of nose, location of chin, right? So we know not just one correspondence, but many correspondences between the two images. So if we know, for example, let me call the reference image x1, y1, okay, and let me call this point as x2, y2, okay. So same way, or you can think of x1 of 1, y1 of 1, x2 of 1, y2 of 1, so that's the left eye, right? Same way, if I go to the right eye in the reference image, let me call it x1 of 2, y1 of 2, and very similarly over here, let me call this incoming image x2 of 2, as far as the right eye is concerned. Okay, those are the coordinates. Okay, so same way, if we know 5 of these, or 6 of these, or 10 of these correspondences, given this information, set of x2s, y2s, set of x1s, y1s, how do we know how much to rotate, how much to scale, how much to shift? So that's the challenge. If we can develop the mathematical theory for it, then we can solve for AB T1, T2. Once we know AB T1, T2, we'll apply it to every pixel over here and then cut out the corner. If this is, for example, 100 by 100. Okay, so once we apply this transformation, what will happen to this particular image is, this will look like, so after we apply AB T1, T2, it will become something like this. Okay, it will become straight, the face will become bigger, same as our reference image. Then the last step we will do is, if this, we know reference image is 100 by 100, we'll just cut out 100 by 100 over here. And then now we will do the recognition based on the registered image. Okay? Okay, so now let's go to our challenge. We know the correspondences somehow, meaning once again where the eyes are, nose is, chin is, and so on. How do we, from this knowledge, how do we know AB T1, T2? Okay, so now we'll go into an important theory. Okay, let me put this information over here, somewhere over here, so that we can come back to it. X prime, y prime equal to AB minus BA. XY plus T1, T2. So that if we know AB, we'll apply to this to make this image look like this, then we'll cut out same as the reference. Okay. So okay, so coming back to our challenge. Okay, the way we can solve this is, this challenge can be solved by a mathematical technique called linear least squares optimization. Okay, so some of you who are in the deep learning class, I went through it. Some of you are not in that deep learning class. I'll quickly review it so that everybody knows. But the difference is in the deep learning, we just saw this for how do we use this information for curve fitting. Here, we will use this technique for parameter estimation, and what are our parameters? A, B, T1, and T2, okay? But as you will see, the steps are exactly the same as we did it for curve fitting in the deep learning class. Okay, so anyway, what does this technique look like? Let me sidetrack and first just talk about linear least squares optimization technique. Once you understand it, then I'll come back and apply to this one. And as part of your second assignment, you'll finish this optimization. You'll actually apply it on images and see what a fantastic job it does. Okay. Anyway, so as far as linear least squares technique is concerned, okay, two important concepts over here. The goal of this technique is to estimate parameters of a model given some data. Okay, so let's take a look at a simple straight line fitting problem. Okay, suppose somebody gave you a few points. Okay, and there could be noise, right? So your goal is this little bit here. Okay, so your goal is to come up with a straight line which does the best possible fit. So a straight line through all these points, so that the error between the given point and the point on the line is as small as possible. So this is where the optimization come into play. Anytime we deal with optimization problems, some of you who were in the parallel computing class where we did a lot of optimization problems, you'll remember what we do is we set up a cost function. Okay? Once we have a loss or a cost function, then we try to minimize that cost or minimize that loss based on our model parameters. Then once that cost is minimized, then we know what are the model parameters. Okay? So for a straight line, our model is very simple. AXI plus B, okay, or Y of I. So every point is given. So for example, 8 is the slope over here. So let's pick one point on the line. Okay, suppose here's the point on the line. Okay. Suppose for x of 2, this happens to be, let's say, 1.8. Okay. So in this example, x of I will be 2. Okay. If we know the slope, we'll plug in slope over here. B is the y-intercept, we'll plug in over here. So this will give us an answer of 1.8 as an example, right? Okay, so, but we don't know what A, what B is. So that's where this linear least squares optimization comes into play. Its job is to let us know what is A and B. If our goal is to fit this data by a straight line. So our model parameters in this straight line example are A and B. So we have to determine A and B. Once we know A and B, we know the exact equation of the line. Okay. So the way we will do it is we'll define a cost. Our cost will be sum over all the points, all the data points that are given to us. Okay. AXI plus B minus y of I. So if I move the y to this side, that will give me how much is the error. Okay, so again to explain this, okay, let's go over here. Okay, let's take a look at one data point. So this is the actual data that's given to us. Okay. Suppose at x equal to 2, the data point that was given to us is not exactly on the line. It's a little bit below the line, right? So if I plug in x of 2, let's pretend in the beginning we estimated a to be, let's say, 0.7. Okay, if a is 0.7, let's pretend b was somehow found to be 0.2. Okay, then if I plug in x of 2, what will it give me? 2 times 0.7, 1.4. It will give me 1.6. But what is the actual point on the line? 1.8. So this is our y of I. Okay, so what's the error then? 0.2. But the error could be positive if or negative. So that's why we always square it, so that we can get a good idea of the magnitude of the error. So as you can see, for all points, this is basically the actual point on the line. Okay, and this is giving us the error so that we can come up with as low of a cost as possible. Okay, let's forget the square. Okay, so anyway, now let's go and so once we have a cost function, then in the linear least squares, what we do is we apply partial derivatives to come up with the model. So our approach will be, suppose I call this C, partial C over partial A, we'll set it equal to 0. Partial C over partial B, we'll set it to 0. Okay? C is the cost. Or let me call it, rather than a cost, let's call it a loss function. So in the terminology, sometimes we use loss, sometimes we use cost, sometimes we use error, but they all mean the same thing, it doesn't matter, okay? So suppose, because you might think A, B, C is something else, but L is our loss or the error function, right? So this technique, all it does is once you have a loss, you do the partial with respect to each of the model parameters, set it to 0, solve that equation, and you will know A and B. So anyway, if I do partial A over partial A equal to 0, what will happen? The 2 will come in over here, correct? AXI plus B minus Y of I. Then further, the inside, I'll take partial with respect to A. So what will I get?
XI, input.
XI. Right? And then sum over all the points and set it equal to 0. Okay. Let's go to the second equation. What will happen to the second equation? Again, 2 AXI plus B minus YI. And then take the derivative partial with respect to B. 1. So this is just 1 equal to 0. Okay. So if I expand out the first equation, what does it become? 2
AXI squared
AXI squared plus B 2B x of I minus 2 xi yi equal to 0.